Hello everybody, dear colleagues, students and guests, and of course, dear Professor Jens Nørskov. Welcome to today's Ørsted lecture, DTU Ørsted lecture. And it is certainly, I can hear the sound is going up and down a little bit, but we'll get there. It's really a special pleasure to welcome one of our own to this kind of thing. Professor Jens Nørskov is, as I'm sure you are well aware of, an internationally outstanding and influential researcher at the highest level. And I think this was confirmed, and it has been confirmed many times, but latest it has been confirmed, if one ever should doubt it, by the award Niels Bohr International Gold Medal, which was presented to Professor Nørskov by Her Majesty the Queen Margaret in October this year. Professor Nørskov was therefore the obvious choice for us for this DTU Ørsted lecture. Yeah, dear Jens, I had the pleasure also of saying a few words at that occasion, or the dinner there, more to be more specific, or close to that with the medal award ceremony. And although you have heard it already, I want to say, just repeat a few of the words again, because they are still as valid as they were the other day, of course. Often, basic and applied science are seen as contradictory or mutually exclusive, but they are, of course, complementary rather than that. And the research of a person like Jens is certainly a very, very fine example of this. Your research, Jens, has distinguished itself by having an unusually broad scope, going all the way from basic quantum mechanical descriptions of electronic behavior and materials to the prediction of new useful materials for sustainable energy and environmental protection to the benefit of society. And along this broad scope, you have excelled in pioneering work. So today, your concepts and models are used in science as well as industry very broadly. Your work on catalysis will be essential, we believe, for our sustainable future, and therefore it is certainly a must for us to know about it if we are to succeed with our sustainable energy perspective of the world. You have many qualities. One is scientific curiosity. You have engagement in what you do. You are really the personification of academic excellence at the highest international level. But I also can say for sure that you are very generous with it all. It's essential for you to share your knowledge, to create strong career environments for young researchers in your field. And in that way you really catalyze the process as a person among other people, as the excellent researcher you are. You foster collaborations and open exchanges, so we all gain more insight, and you share that insight and make good use of it, certainly for the benefit of science, for the benefit of society, and therefore certainly very much in the spirit of our founder here at DTU, Hans Christian Ørsted. And I should also like to mention that thanks to a generous donation by Willumfonden, we had also the great fortune here at DTU to welcoming you back here to DTU from several years that you have spent equally successfully as the rest of your career at Stanford University. At DTU you will, I'm sure, among many other things that I cannot even think about or guess about today, but I'm sure you will establish a new world-leading catalysis center, and we are certainly very proud to have you back, Jens, and to be here and make this your playground for your continued work, which I'm sure will have great impact on our society and holds great promises for our future. So I'm sure also that Niels Bohr's international gold medal could not be in better hands. So I don't want to take more time. I'm sure you came here today not to listen to me, but to Jens, and so you will. So I just want to say a warm welcome, Jens, here to talk, and a warm welcome to everybody to listen to all the wise words of Jens. We love to hear what you have to share with us. So thank you, everybody, and welcome. Thank you.
Thank you, Anders, for the kind words. Thanks to everybody here. It's really great to see so many old friends here. And I can only say I'm very happy to be back here at DTU, my real home in many ways. So I'm going to say a little bit about what we're trying, we and many others, I should say, are trying to understand better, and that's anything related to the way in which we can transform the energy input from the sun into some chemical form that can be used as a basis for energy storage, but also as a basis for our chemical industry. And this is the main thing that I will be talking about. The outline is here. I'll say a little bit about the background, namely, why do we need chemical energy transformations? Then I'll say something about the challenges we have, scientific challenges we have before we can get there, and then get back to, shall we say, the real topic, namely, how can theory help here? And I hope I'll illustrate that. So first, a few words about chemical energy transformation. So the last century, the 20th century, has really witnessed a fantastic revolution in our lives, and all of that is a tribute to chemical science and chemical technology. So the fact that all of the products that make the foundation for modern society, all the way from fuels to fertilizers, all kinds of materials, pharmaceuticals, all of that relies on our ability to transform fossil resources into model products that can be turned into these products, or model, shall we say, chemicals that can be transformed into these products. So our lives today is only possible because of this chemical technology, and so that's been a big victory for science. The backside of that coin, of course, is that it has an impact on climate. So what is shown to the left, you all know this, but I think this is a very nice way of illustrating it. Actually, one that Joe Gautier, one of my students who's sitting right there, found. What you're seeing to the left is the temperature, average temperature in the world, month by month, since the middle of the 19th century. And you see that when we get close to now, then all of a sudden it explodes, and that is correlated with the fact that the CO2 level is going up here. So we are in the middle of a huge experiment. What will happen to the climate, we don't know actually, but I think it's very wise to try and find ways to limit the emission of CO2. And in fact, we need to do more than that. This is illustrated here. These are 5 scenarios of our future from the latest IPCC report, showing what kind of reductions in CO2 emissions we need in order to stay below 6 degrees C, 5, 4, 3, and 2 degrees C. And the point to notice here is that according to these models, if we want to stay below 2 degrees C, then we're not just talking about limiting or lowering our CO2 emissions, we're actually talking about having net negative CO2 emissions. We actually need to capture more CO2 than we emit. And that puts some very, very big challenges to us all. Now, there are some good news, some very good news, in fact, and it's illustrated here. If you look to the left here, what is shown is the average price, that's the dashed line here, of electricity from wind turbines as a function of time in the last 8 years or so. And what you notice is a sharp decrease, and this red horizontal line, that's the price of electricity from a modern natural gas-fired power plant. So it has actually crossed through about a year ago. So we actually get cheaper electricity from renewable resources than from fossil resources today. Let me just point out that if we had talked about coal-fired power plants, it would be up here, not down there. Now, the same is true for photovoltaics. There are two lines here, or two dashed lines. The lower one is for utility scale photovoltaics, and the other one is for photovoltaics, the kind of things that you have on the roof of your house. Again, for utility scale, it is crossing now. For the rooftops, it'll take a little while yet, but the trend is definitely there. So we can actually make electricity from sustainable sources cheaply. The problem is that it basically comes as the wind is blowing. So we need to be able to store energy. And that is the biggest challenge that we have right now for a sustainable energy future. Let me talk about two important ways here. Batteries is the obvious solution. You directly store the electricity there. And we have existing technology that works with a high efficiency. Lithium-ion batteries do work. They are in cars, and they do have a high efficiency. The problem is that the energy density in batteries is still, today's batteries, is very low. It's illustrated down here. This is the energy density volumetric and gravimetric here. You have the energy density in fuels, diesel, jet fuel, gasoline up here, and batteries is down there. That's why you need, when you buy a Tesla, you get an extra half a ton of battery to drive 400 miles or whatever it is today. The other, shall we say, issue here is that we will need a completely new infrastructure, and that's not going to be cheap either. But this is definitely part of the solution. We would dearly like to have a higher energy density, and there's a lot of research here and elsewhere in the world trying to come up with new battery chemistries, because we need completely new concepts here to solve it. The other option is to actually make these fuels, the high energy density fuels, directly by making them synthetically, that is, by making them by using the electricity to drive chemical properties to make fuels. We have already seen the energy density is high. We do have the infrastructure. There's another benefit here, and that is the fact that about 10% of all the fossil energy that goes into the energy system today goes into making not fuels but chemicals. So we need feedstocks for everything that we make, apart from fuels, and that we would get directly if we had such technology available. The reason we don't see a lot of this, you can do it today, but the efficiency is low. And I'll get back to why that is. So the issue that I will be mainly addressing here today is this question of the low efficiency of our chemical electricity to chemical energy and vice versa conversions here. So what we would dearly like is to be able to close what's known as the carbon cycle. So what we are very good at today is to take a fuel that is a high energy, molecule and combust it and use that for driving and for everything else, we emit CO2. What we would need to be able to do is to harvest the CO2, and that's a whole problem by itself. I'm not going to talk about it here. And then reduce the CO2 to get back the fuel. So we take a very stable molecule and we put energy into that and make new chemical bonds that are not very stable so that we can gain a lot of energy by combusting it. That's the challenge that we have. So what we really need is a new landscape where we have what you could call e-refineries or electron refineries, where the input is electricity from sustainable resources, water, CO2, and nitrogen if we want to make ammonia for agriculture. But then we should, in principle, be able to make everything that we had before. Use the infrastructure, use the industry we have, but with an input in terms of energy that is sustainable. That's the dream. That's what we need to do. How would this, the core of such a technology look? Ideally, it would be something like this. It would be an electrochemical cell. We would drive it by supplying a voltage coming from sustainable resources. And on one electrode, we would split water, emit oxygen, and then take the protons, and they can go through an electrolyte there. We drive it by pulling the electron through, and at the other electrode, we can either make hydrogen directly by recombining protons and electrons, or we can reduce CO2 to fuels, or reduce N2 to ammonia that can go on both as a fuel but also as fertilizer and a source of all the nitrogen compounds that we need. So these are the fuels and base chemicals. And in reality, this is basically what photosynthesis does in nature, capturing CO2 and using the solar influx to reduce the CO2, in that case to a sugar, but the basic principle is the same. So this is what we would like to do. Now, well, let me say one more thing, by the way, here. It would be ideal, of course, to take, say, CO2 and directly make a fuel here. But even if we can only make hydrogen, then if we have the hydrogen, we can use conventional thermal catalysis to make fuels again. And this is known technology, but we would probably need to do this under conditions that are very different from today's technology. Because today we have basically industry that lives off large amounts of, say, natural gas or gasoline or crude oil, and it's very centralized production. If we use solar panels or wind turbines, that's very distributed. There's no reason to have very centralized facilities. There's also no reason to have very high pressure processes. Typically, making methanol, for instance, you run at 80 bar. If you make ammonia, you do 100 or 150 bar. And that is, shall we say, very expensive equipment that you need in order to be able to do that. So we would really like to get new conditions, lower pressures, and that actually always means, in these cases at least, lower temperatures, and that means new catalysts. So, what are the challenges? Well, let's start. We can make hydrogen today quite efficiently, but basically using or based on platinum and other scarce, very expensive catalysts. We can also split water and emit oxygen, again using very expensive catalysts, and they are incredibly poor. I'll show you that in a moment. If we want to reduce CO2, though the catalysts we have today are even worse, and the worst ones are those that can reduce N2. And that sums up where we are, unfortunately. So what has been happening in the last decades is a lot of, shall we say, trial and error experimentation to try to find better catalysts. And that has only taken us so far. I'll illustrate it here. This is a summary of some of the best catalysts reported in the open literature for oxygen evolution, that is water splitting to emit oxygen. And what is shown here is the so-called overpotential. That's the extra potential you need to apply in order to make this happen at a reasonable rate. And so this here is a measure of the energy loss in this process. And these are papers from the last 10 years or so. And it's not that these are sort of obscure things. These are things you see in Nature and Science, and you see press releases and whatnot for each one of these. But when you plot it like this, you will probably agree with me that not a whole lot has happened. So it tells us two things. First of all, that there's something quite fundamental that prevents us from having better catalysts, and that probably it would be a good idea to understand what that is in order to really try and break this unfortunate trend here. Can illustrate the difficulty, the even larger difficulty we have in reducing CO2. What is shown here is the current density, or that is the rate, for making C1 products, that's methane, and C2 products, that's primarily ethanol, as a function of the applied potential. Here are the equilibrium potential, the green here, for instance, for making methane. And the difference in potential here and the potential at which you see an appreciable rate, that's again a measure of the loss. That's an energy loss again. And you can see that here losses are in the range 1 volt. So 1 EV in loss per electron used. If you want to make methane, you need 8 electrons, so that's 8 EV, that's 800 kilojoules per mole of methane that you're losing in making that. That's not good. So the challenge here is even larger than for the water splitting, and actually you have to do both. So, sorry. Now, if we want to understand how these things happen, then we usually calculate a free energy diagram like this, showing how there are activation barriers separating each of the intermediates in a process, in this case, taking CO2 all the way to make methane. And these are calculations by a number of Xinyan Liu, and Karen Chan is actually sitting here. This looks fairly complicated, you would agree, but this is just to make one particular product. We can make many products. And that means that there are many pathways like this. In fact, if you make an overview here of the ways in which you can take CO2, CO2 and hydrogen and make just 4 different products. You always make water, but you make methanol, acetaldehyde, methane, and ethanol. That's just 4 products. Only the C1s and one of the C2 products, two of the C2 products you can make. Then these are the different ways you can do it. So each line here is one reaction pathway. And so what it illustrates is that we're looking here at problems with an enormous intrinsic complexity. And that explains, I think, to a large extent why catalysis is often viewed as sort of a black box or black magic, because imagine that you wanted to design an experiment to tell you which way you did this. That's not so easy. And if you want to have sort of a rational approach to finding better catalysts, then the number of activation barriers you would need to know is in the hundreds. So we need some guiding principles here. And this is where theory comes in, I believe, strongly. So let me just say one word here about what I mean by theory. By theory, I mean the concepts that allow you to think about both theory, both experiment, but also what is sometimes confused with theory, namely computational methods. For decades, we've had experiments and then theory to test experiments and make predictions to new experiments and building up such an understanding. What has happened in the last, say, 20 years or so is that computational methods, solving the Schrödinger equation to get real information about processes has risen exponentially. And we can actually today do calculations in a reliable way. And what it really gives us is something more akin to experiment than to theory, in the sense that these are basically computer experiments. But they allow us to get a lot of information that we can not get easily from real experiments. We can, for instance, vary parameters much more freely in much more idealized situations too than we can in real experiments. And I'll try and illustrate it a little later. It, of course, means that our computational methods need to be benchmarked very, very well against experiments. And that's something we do all the time. In fact, I'll illustrate it here, just in case you don't believe me. What is shown up here is a comparison of errors, mean absolute errors or mean signed errors. It's simply a measure of how far our calculated results, in this case for bond energies of atoms and molecules to surfaces, compared to experiment. Actually, what we did was we allied ourselves with some of the best experimentalists in the field, and you would think that there would be a lot of good data out there. In fact, there's very, very little. But we have tried to find whatever there is, very well characterized systems where we know exactly what the bond strength is. And all I want to point out here is that there are early versions of theory where errors are very large, but in, shall we say, modern versions, errors are actually of an acceptable size, to a point where we can make predictions and we can understand trends. The same is true for activation barriers. Again, we had to look hard to find good experimental data. I can actually say that the postdoc who did this, she came one day and she said, why is it that most of the good data I can find, really good data, come from this guy, Chorkendorf, Ib Chorkendorf. So we can be proud of that here. So what is shown here is a parity plot, theory versus experiment, again showing that we do pretty well. We do pretty well. Okay, so getting back to this free energy diagram, let's focus on one activation energy here, the one to add a proton and electron to carbon monoxide sitting on a surface in order to form the first hydrogenated form. That's one of the more difficult steps in this process. And what I'm showing here, is a bunch of activation energies for different catalyst materials plotted as a function of the bond strength of the carbon monoxide to the surface. Let me just point out here one interesting aspect. What you see here is that this bond strength varies by more than almost 3 eV. You could never do experiments in a range like this. So the approach is you benchmark your theoretical or your computational, I almost did the mistake here, the computational results against the experiment, but then you can use the computer to actually show data for a range of materials where you could never do experiments properly. Anyhow, what you're supposed to see here is that there is a clear correlation between the two, what we call a scaling relation. And what it means is that if you know the ability of your catalyst surface to bond carbon monoxide, then you also know roughly what is the barrier for the first hydrogenation step. Now, that's already a simplification, but it is not just for this process. These are other processes, these are thermal processes, but it doesn't matter. This is the barrier for adding the second hydrogen to a carbon atom on a surface, going from CH to CH2, plotted as a function of the bond strength to carbon monoxide. Again, different materials are put on here as catalyst, and you see this scaling relation again. If you want to add an OH group to CH, then again you get a linear scaling relation, but now it's a linear combination of the ability to bond carbon monoxide and the ability to bond OH that is the descriptor. That's not so strange, because in this case all of the chemistry is between carbon and the surface. In this case, both carbon and the oxygen end interact with the surface in the transition state. But again, you have linear relationships like that. And in fact, if you go through reaction elementary step by elementary step for a whole bunch of these, then you find these linear scaling relations everywhere. They seem to be a very, shall we say, universal aspect of such surface reactions. They are known in chemistry, or one form of these has been known in chemistry, known as Bronsted-Evans-Polanyi relationships. That's relationships between transition state energies and reaction energies. This is a generalization of that, but it seems to be very, very robust. And what it really means is that instead of having hundreds of independent parameters, we have only a few, in this case of the order 2, independent parameters, and all of the others are functions of those independent parameters. That's an incredible simplification. And that allows us to begin to think more rationally about what makes a good catalyst and what makes a less good catalyst. And if we go back to the question of electrochemical CO2 reduction, then one of the things that you have seen already is that the ability of the catalyst surface to bind carbon monoxide is a good descriptor for a lot of these processes. In fact, all of those that are important here. And what it means is that we can show the rate and plot it as a function of this parameter, and that actually allows us to, shall we say, rationalize a lot of the insights that we have from experiment. These are experimental data from the group of Tom Jaramillo at Stanford, plotted as a function of the calculated carbon monoxide bond energy. And you see a nice trend. This is a model, a very simple model that Karen Chan and others have developed to describe this. So this, all of a sudden, we can begin to look at the ability of different materials as a catalyst as a function of something we can understand. And we can even say, well, the optimum seems to be just around here in terms of the ability to bond carbon monoxide. The really sad part of this is that copper is known to be the best we have, and you just saw how bad it is. And that seems to be close to the top of this volcano relationship. That's not so nice. I'll get to what might be, how we may need to think about this later. Now, these, the fact that once we realize what a good descriptor of catalytic activity is, then we can begin to play around on the computer to see if we can find new materials. And we already talked about briefly that for making hydrogen, the simplest fuel that you can make, recombination of protons and electrons to form H2 molecules, it's actually known and has been known for years that the noble platinum group metals are good catalysts, and that's shown here. Here we have experimental data from many groups around the world over many, many years, plotted now as a function of our calculated hydrogen adsorption energy to the surface. And you can see that you have an optimum which is right there where the noble metals are. That's known. Now what we could do is, well, we could then search for materials that were kind enough to have hydrogen adsorption energies that was close to the optimum here. And it turned out that molybdenum disulfide here, that's a sandwich structure with molybdenum in the middle and sulfurs on both sides, that actually is not so bad. It's not as good as platinum by far, but it's not so bad. And it has the nice property that it's cheap and it's very stable. I should say it's actually not the basal planes of these 2D materials that is active. It's actually the edges. And that was also shown experimentally in the group of Ib Kogendorf. The point is now that then if you want a good catalyst, you take molybdenum disulfide, then you nanostructure it to expose as many edges as possible. And that has been refined in the literature now, hundreds or thousands of papers now each year. But the point is that here's a case where the energy loss that we used to see for non-platinum based materials has really gone down in the last 5 years or so. Simply by going to these much cheaper materials, loading a lot of it in, and having a lot of edge sites so that we expose a lot of these active sites. It's a different strategy, but that actually works. Here's another example. This is the rate for making methanol from carbon dioxide and hydrogen, plotted as a function of, again, of a descriptor of the catalytic activity. You have the elemental metals as catalyst here: palladium, copper, nickel. Copper is closest to the best, that's known. It's a copper-based catalyst that is used. You can add zinc here, and it gets a little better. That's done. That's the commercial catalyst is a zinc-promoted copper. But you can also see actually other materials now, new materials, nickel gallium, for instance. Various alloys were suggested from this to also be good catalysts, perhaps as good as the copper zinc. And there are experimental data here from, again, the group of Ib Kogendorf, Søren Dahl, showing rate as a function of temperature. The yellow is something close to the commercial catalyst. And the red here is one of these intermetallic nickel gallium compounds, which is as good or perhaps even better than the copper zinc oxide catalyst. So you can use this. Once you realize what the descriptor is, then you can begin to use the computer to search for new materials. This happens. Okay, but let's get back to this challenge that I started by talking about. I showed this in the beginning. This is the overpotential, the energy loss for different catalysts for the oxygen evolution reaction, water splitting to form oxygen. And what was observed here was that in spite of a lot of work, very little has happened. Try and look over here. What is shown here is a simple model of the overpotential, a theoretical model, in a color code such that deep red is where there's no overpotential, very low energy loss, and blue is where the energy loss is large. And it's plotted here against two different descriptors. It's not very important what it is, but it's the ability to bond two different intermediates in this process. And obviously, if we could vary those independent of each other, we should be able to get there, and then we would have a good catalyst for water splitting, and we could do electrolysis without any energy loss. The problem is that these are calculations now for different materials that are known for the being used for these, and you see that there is a scaling relation between these two parameters. We cannot vary them independently. So I would suggest that it is highly likely that what is happening when people look and try new materials all the time, that they are optimizing, but they are optimizing running up and down this line here, way off the actual optimum. And that really calls for then a totally new way of thinking about how to make catalysts for this process. Here's the opposite reaction, the oxygen reduction reaction. That's where you reduce oxygen to form water and electricity. This is what happens in a fuel cell at the cathode. And the picture is exactly the same. You have an optimum here. You have all the materials that people usually use up here. Platinum is that circle right there. You can new fuel cells like the one in the Toyota Mirai, they're actually using a nickel platinum catalyst. That's one of those here. And you can see it is better. But we're really optimizing far away from the optimum. And again, if you look over here at the overpotential, the loss as a function of time in the last 10 years, the story is exactly the same. For probably exactly the same reason. Same thing, if you look, sorry, it's really fast this. If you look at CO2 reduction, again, you have materials that are running in the foothills but never get close to where you would really like to be. N2 reduction, exactly the same thing. Optimum is here. You can see there's sort of a little red dot here. That's where you would like to be. And all the materials we know and have been tested, they're up here, way off the optimum. These are two different descriptors, but it doesn't matter. This process has another interesting, or shall we say, challenging aspect to it. If you look at some measure of the rate here as a function of the descriptor, that is when we just move up and down this line, then there's an optimum here, and the black here is for reducing nitrogen, reducing N2. This here is for making hydrogen. And you can see that it always has a much higher rate for making hydrogen than for reducing N2. So when you run it, all you get is hydrogen out and no ammonia. So that's a selectivity issue that we also need to control. Okay, solutions. Well, what I've been trying to illustrate is that we would dearly like to be able to control two different parameters independently, but these scaling relations, they prevent us from doing it. Now, where do these scaling relations come from? They come from the fact that if we adsorb something on a surface and you bond, say, through the oxygen end, then that bond is the same whether that is oxygen in OH or in OOH, for instance. What it means is that you can vary one, and then you vary the other bond strength by exactly the same amount. You get nowhere. So what we need to is for some way in which we can, shall we say, a system that can tell the difference between what is in the other end of the molecule. So we only see, or the catalyst only see the oxygen end, but we need to know what is in the other end. That is, we need another dimension in the active site. That's what you have in enzymes, for instance. Enzymes use the whole 3D structure of the enzyme to stabilize transition states for certain processes and not others. So we need to be able to sort of have new kinds of active sites that have more functionality, or to have sort of 3D structures, to have ligands, things that we can also learn from homogeneous catalysis. We need to invoke all of that, I believe. One way or another, it's not simple. I'll just give one example. This is a purely hypothetical one, because this has been done on the computer by Charlotte Kirk here and Lian Chen. Again, you'll see Karen Chan is the key person here. The idea is to, instead of using these metals and metal surfaces as a catalyst, to use graphene doped with transition metals in single vacancies in the graphene. We just need somebody who can make this, and only make this. But if you look over here, there are actually dopants that ought to get us into the deep red region, where CO2 reduction to methane, in this case, should be possible at a reasonable rate. So we are hoping somebody will be able to make this and keep it stable. That's the other big challenge here. We'll see. So either we need to go to new classes of materials. The other possibility is to find completely new processes. And let me illustrate it here. If we want to reduce N2 to make ammonia, I just showed you that there's a preference for making hydrogen instead of ammonia. The reason is actually quite simple. I won't go through the math here. I'll just explain it to you. When we run the process, there are two possibilities. You have an active site on the surface. When you are at negative potential, you can attract protons and adsorb hydrogen, or you can attract N2 and adsorb it. At negative enough potentials, you'll always get hydrogen in there. If you have hydrogen sitting, you can attract another proton and an electron, and you form H2. That's what you don't want. So you want to be able to cover your surface with N2 and not hydrogen. How do you do that? You have to actually restrict your access to protons or to electrons, or both. And you can think of various ways of doing that. Some of them are illustrated here. You could actually, for instance, use a non-aqueous solvent. Then you don't have a whole lot of protons. Or you can limit the access of electrons. By the way, there's an enzyme, nitrogenase, that can do that. There the strategy is actually to limit the access of electrons. And here are some experimental data from Ib Korgendorf's group again, and a whole lot of other folks, both at Stanford and here, a big collaboration funded by the Willum Foundation. But what you can observe here, just forget about all these here, but these are two different catalysts. One run in an aqueous solution where you have lots of protons available, and one run in a non-aqueous solution where you can limit that. And what the Faraday efficiency, the percentage here, that's simply the percentage of the electrons that go into making ammonia instead of hydrogen. So you can go from 1 per mil or less than 1 per mil to actually 10 or 15% by switching that access. So this is simply making another process. And here's another way of doing the same thing. You want to do the reduction, add the electrons, without having any access to protons. So why not just separate it completely? So here's a process. You take lithium hydroxide, you apply a potential, you deposit lithium. Then you expose that to nitrogen that reacts thermally at room temperature to form lithium nitride. And then you expose that to water, you get back the lithium hydroxide and ammonia. That we have developed, and that gives about 90% efficiency towards making ammonia. So you can actually play these tricks in a very simple way here. Here the challenge is, of course, that now you need to have a cyclic process where with different chambers to do it. So there's a big engineering challenge here that some people are trying to take up now. So I'll just skip this and go directly to the most important part here, namely to show you that a lot of people contributed to what I've been talking about here. This is the theory group at Stanford last year at an outing. And I just want to point out some people here. I already mentioned Karen Chan several times. She's actually, since 2 weeks, an associate professor here, and she's sitting right there. You can wave your hand, Karen. And you can ask her all these questions that you may have here. Perhaps not now, but later. And 2 students, Lian Chen and Xinyan Liu, did all the CO2 work. Karen was in charge of all of that. The oxygen electrochemistry, Charlotte Kirk, Colin Dickens, and Joe Gauthier. And Joe is also sitting here, ready to answer any difficult questions you may have. The hydrogen work has mainly been Charlie Tsai here, and also Yong Fei here. And then 2 of the senior scientists at SLAC that have been part of running a lot of this, Thomas Bligård, who actually used to be an associate professor here, and Frank Abel Petersen. Apart from that, a number of people from the group has gone out and made careers elsewhere, and you can see a lot of people, some of which you will recognize, collaborators with Carsten Jacobsen, for instance, Jan Rosmeisler, you know, Björk Hammer. And then, very importantly, collaborations with experimental groups who've been kind enough to tell us when we're wrong and test out ideas. Ib Korkendorf and Jakob Kipsgaard here. Tom Harmeo's group at Stanford, Anders Nilsson at Stockholm University, and also a number of people here from Haldor Topsøe who have been kind enough to collaborate over the years. And finally, let me make sure to point out, who paid for all of this. The US Department of Energy has put a lot of money into this through 2 different entities here, and most recently the Willem Foundation, through a number of grants here to DTU, are now footing a big part of the bill. And then thank you very much for your attention.
Thanks to Jens for this nice presentation. So my name is Carsten Jacobsen. I'm from the Department of Physics here. And I will be chairing a session with questions now. Any questions to Jens? Or Karen, if it was difficult, or how was it?
Exactly. Karen and Joe.
Hi Jens, what a wonderful talk. Thank you very much. Can you say anything about how, I mean, the sun hits the earth and it ends up as heat anyway. And I think it's also a big waste in the biosynthetic.
Yeah.
So biosynthesis. So what is the price per solar generated kilowatt or something that is low enough that you can afford the waste of energy that your overpotential gives rise to? Can you say anything about that? Is there any, is it anywhere in sight?
I mean, let me perhaps try and answer it a little differently, but then you can make a protest here. We are never going to get fuels, synthetic fuels, that are as cheap as what you can pump out of the desert in Saudi Arabia. I can promise you that. So there's going to be a price for this, no matter what. I think we can make electricity, but storing it and doing all the other things we want to do, there's going to be a price. The question is only how high a price. And how high a price is acceptable, that's up to everybody in the end. That's a political question. This is something that our politicians need to get to terms with, I think. I don't know if that answers your question, but I mean, there is a price, without a doubt. Now, in nature, perhaps you can live with a fairly high price. The efficiency is very low, less than 1% of the influx ends up as energy in plants. typically. We need a higher efficiency because otherwise we would have to have as many solar cells as we have arable land now, and that would not work. So we need quite a bit higher efficiency. We also need better stability, by the way.
You ready?
Hi. While we impatiently wait for this amazing research to advance, how do you rate the possibility of swapping the solar and wind energy with nuclear power?
I think that nuclear power will be able to provide, shall we say, if not sustainable, then at least electricity without any CO2 emission. That was probably not what you were asking, but that's obviously the case. On the other hand, whether that will be societally acceptable is a different question. There is still a waste problem, which is not CO2, but something else, even worse, probably.
Professor, thank you for your talk. You mentioned a lot enzymes, and they've also been quite fashionable over the past few weeks, given the Nobel Prize in Chemistry. Do you see enzymes as having a practical role in enabling these transformations, and what would be the challenges to make that possible?
Well, I mean, enzymes do this all the time. Photosynthesis happens all the time. Any sort of bio-based either fuels or chemicals use that all the time. I think the main problem there is that the efficiency is quite low. So you need a lot of area filled with that. And one of the issues we have is there enough? And the competition with making food for all of us. So there are many issues. I do think that biomass will be a very important part of the whole scenario moving forward. But it probably cannot stand alone.
Thank you for the talk. With regards to the doped graphene you talked about and how it was able to overcome the scaling relation, do you know why it is that this doped graphene is actually working so much better?
It's a good question. What we think is that it is mainly due to a larger flexibility of a site like that. You actually need for the CO to be able to bend over so that a proton can attack. And these sites are very different there from shall we say, planar metal surfaces in that respect. You have a much larger ability to rotate. Yes.
Hi Jens, thanks for a great talk. So it seems like
the sound came from behind me, so I'm just confused for a moment.
So it seems like whenever we have a scaling relation, we are never hitting the optimum. Are we simply just unlucky with the reactions that we are looking at?
Well, I mean, for hydrogen evolution, we do.
Yeah, but there we only have one intermediate.
Exactly, yes.
So if we have two, are we just always unlucky?
I wouldn't promise that we're always unlucky, but there is, of course, a good reason why it is so difficult and has always been so difficult to find good catalysts. And I think this is one of the reasons. That's at least one way of describing that inherent difficulty, namely that it's always a balance between being able to do one thing and then do another thing, which is part of the total reaction. And then on top of that, we always have stability, by the way. But I don't think there's a conspiracy here, but it is inherently difficult to optimize many things at the same time.
Well, if you draw a line in the plane, what's the probability that it goes through a particular point?
I'm sure you could calculate that easily. Yes.
Hi, thank you for the presentation. You talk about electron immobilized nitrogenases, and you talk about also molybdosulfides as a possible metal. Have you looked into molybdo enzymes that have been shown to reduce CO2?
I mean, we have also tried to understand that system, and many have, of course, worked much more than we have. I mean, my present understanding, which is limited, but my present, shall we say, understanding, interpretation of what I see is that nitrogenase is exactly in one of these 4 quadrants that I showed, where you're limited by the electron transfer. So what it means is that for most of the time, the active site is one that does not have a bias, that does not have electrons there, and therefore N2 can adsorb very readily. Then the N2 sits there, and when the electron gets transferred, then the proton will attack the N2 and not become adsorbed as a hydrogen atom. So I think it actually fits very well with the picture that we are developing now of what it takes to make a highly efficient, in terms of selectivity, catalyst. It's actually a fairly poor catalyst. So is nitrogenase, by the way. You need an enormous potential to drive it. So, yeah.
Any more questions? Okay, let's have a last one.
I wanted to use the mic, but I also have a question. So when we try to find new catalysts, all that we are doing is moving along one scaling line. Now, if I want to move my scaling line more in the dark red region, so am I changing the mechanism or just some kind of interaction like in doped graphene case?
I think first of all, along these lines, you have a continuous change in mechanism, by the way, but simply because you have different rate determining step depending on where you are. That's what gives this volcano-shaped appearance of rate versus the descriptor. But typically, if we shift these scaling lines, it's typically because we change the structure of the active site. So it's mostly that. But structure here could mean anything. It could be in the spin state, or it could be the actual geometrical structure, or it could be that you have an electrolyte that can interact in many ways that you can do it, hopefully.
Okay, I'll have a last question. You have quite a bit of scatter around these scaling relations. Could you just be lucky to have a bit of an outlier? I mean, it's not that many sigmas outside, is it?
Yeah, that's a very, very good question, and you of course even know the answer, right? So, no, I mean there are 2 parts to the answer. First of all, that in these calculations there are uncertainties, and the big question is: this scatter, is it real? Or is it a reflection of the uncertainty? We actually don't know. But what we do know is that the lines are always much better determined than the individual points. Number 1. Number 2, we know that by experience simply that these lines describe trends, experimental trends, very well for a very large number of systems. If you had sort of large scatter around there, that would not be the case. So I think we are in a situation where we are, and this is something that's why I mentioned you know about it. It's a model with an intrinsic uncertainty in the model.
Okay, thank you very much to Jens again. And before you clap your hands again, there will be a reception outside starting now, and you can also talk with Jens out there. You're all welcome. Okay, thanks again to Jens.